All right, welcome back. So for today's class, we have a mismatch of a few things that we're going to work on. I want to finish up just a couple of short things about solar, and then we are going to cover both hydro and wind today. So we're focusing much more on solar than we are hydro and wind because a lot of the innovation that's going on in renewables right now is happening with solar. So I'm sort of putting a lot more into the solar and a lot less into wind and hydro. Um, Also, I am making available your final exam essay assignment on Moodle today. And in preparation for this, I am going to go through some things about plagiarism and citing sources and stuff like that to make sure that everybody's prepared for the requirements of this test, of this final essay. So with that, let's get started. And okay, so last time we spoke a lot about passive designs, so just ways that we can design buildings to better take advantage of a solar resource. We also talked a lot about PV, and I just had a couple follow-up things about PV. So these are some projections from the US government. So they're pretty conservative projections. The government doesn't tend to be super ambitious with these sorts of things. Um, and for forecasts going into the future to see how much oil, this is natural gas is what the pipeline maybe is the PL. I'm not totally sure what the PL stands there. So we'll look at this one, oil and natural gas production in millions of barrels per day. And here's today, this dashed line. So everything to the left, this is observations, and to the right is a forecast into the future. And the forecasts are based on a whole bunch of different assumptions about what happens in the future. So we have a high oil price projection, right? If the price of oil goes high, then oil starts to drop off pretty quickly by 2050. Whereas if we have high oil and gas resource and technology, then we continue ramping up our oil and gas. And still we start to kind of decline by 2050. So for oil and gas, pretty much all of these are forecasted to decline over the next couple of decades. So we're in this exponential growth phase right now. And whether this is peaking because we've hit the peak, like Hilbert's peak, or if it's peaking because we're transitioning to more renewables, it doesn't say. So we'll skip over dry natural gas production and we'll move into renewable production. So here is our observations. We're very much so in the exponential growth phase of renewables right now. And then all of these economic forecasts have renewables ramping up a lot very quickly. So kind of continuing on very much an exponential growth phase where every year we have more renewables, more new renewables than we had in the previous year. Here's some more forecasts from the same government website. Electricity generation by fuel. So today is the dashed line and going forward up till 2050. And you can see coal dwindling and going down, nuclear staying more or less the same, natural gas going up a little bit, and renewables going up by quite a bit. And now let's look in at the renewables and see where that growth is coming from. So again, this portion of the curve is where we are right now. And this is a good thing to look at, right? Where are we right now? Where do we get our renewables from right now? We hear a ton about solar and we see a ton of solar panels up on roofs around. Actually, it's a pretty small part of our energy mix right now. A much bigger part is wind. I think we currently get maybe 3% of our electricity from wind. And then down here is hydro, and then we have other, that could be any number of little things, maybe natural, like landfill gas. Sometimes people will take the methane that comes out of landfills and try to turn that into something useful. And there's geothermal, and you can see solar is this tiny little sliver now, but into the future it becomes a much bigger part of the picture, overtaking the steady renewables like wind and hydro pretty soon. So this is how we compare to the rest of the world, and there's a lot on this slide. I'm going to spend a few minutes on it, so don't feel like you need to look at it all right now. Okay, let's turn our attention first just to this graph here. So this is in 2018 where the PV was. So you can see that probably a third or so of worldwide PV is in China. US is in second, but really far behind China. So we have a tiny fraction compared to China. And then there's Japan, Germany, India, Italy, the UK, and we're sort of going into individual countries. And then we can say the rest of Europe that's not on here is that much, and the rest of the world is this much. If you've ever taken a statistics class in Albany, I think you've been told to not make a pie chart this way. Right, it's much easier to look at a pie chart in terms of percent than whole numbers, so it's a little hard to read this graph, but I didn't make this graph, I just copied it. So some things that are going on with solar right now. So I'm going to talk about these bulleted points now. The solar sector is a huge part of our current energy setup. So it currently employs about 250,000 people, representing millions of dollars of income and billions of dollars of total economic activity. Solar is responsible for about 1.5% of the US electricity in 2018. And the projections are that that should double within 5 years. So if you want to think about that exponential growth type stuff that we were talking about in class a week ago, you can think about, right, so the COVID cases are doubling every 2 to 3 days in New York State right now, right? That is something that tells us how quickly the exponential growth is going up. So the doubling of solar right now is in about 5 years. It's by far the fastest growing renewable, which we've already talked about. The Trump administration has done quite a bit to try to, maybe not try, but has done quite a bit to de-incentivize solar. So one of the biggest things that they did is that the Trump administration, once they got into office, enacted lots of different tariffs. And on the news, you've heard of this as being called a trade war with China. Solar fell into the trade war with China start of things. So we have a 30% import tariff on all solar panels, and that should actually say all solar panels from China. But China is right here, right, the worldwide leader in solar installation, and that also makes them the worldwide leader in solar panel production. So I think over 60% of worldwide solar panels are made in China. And so now it costs 30% more to import those. And at the time when these tariffs were put into place now about a year and a half ago, almost no solar panels were being manufactured in the US. All of these jobs up here were not jobs of people manufacturing solar panels, but jobs of people selling solar panels, installing solar panels, and working on that end of the grid. So like working for a solar panel installation company, not actually manufacturing the solar panels at all. So in the short term, this was hugely costly for the solar industry. And actually, if I go back here, you can even see this little dip. It's kind of too little to be talking about, but we dipped off of we were kind of going straight up, 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 and then we leveled out for a few years. This is the effect of those tariffs. So, right, we have tens of gigawatts of solar installation that were just canceled because they were no longer economically viable, because now the panels cost 30% more, and the panels are a huge percent of the cost to install solar. So the cost just went way up. So in the short term, this was really hugely costly for the solar industry. In the long term, there's starting to be hints that U.S. manufacturing of solar panel is getting into gear and becoming something. So it remains to be seen. In the long term, perhaps we will see a benefit of this, in that we will have more manufacturing jobs here. But just a little example, I think, of how the topics of this class are very much the topics of the world right now. And Yeah, and solar got caught up in the mix of politics in the last couple of years. Okay, so there's the last little chunk I wanted to say on PV. I also want to spend a few words talking about active designs. Okay, so these are designs that we can build that actually do use pumps or fans to move solar energy around. So let's go talk about an example of this. So the people in this house enjoy heated water using a solar thermal system. So this is an example of a flat plate solar collector. And while this may look like a PV panel to you, this is not a PV panel. What is going on is that inside these solar panels is liquid that is getting exposed to the sun and warming up. And so, right, you take you take this kind of hot liquid that's heated up on the roof of your home and you pump it down into your basement or wherever your hot water heater is, and you use that heat to warm your water. And your textbook author claims that even in Vermont, somewhere with a solar resource that is, if it's even possible, far less than the solar resource in New York State, he's able to get 90% of his hot water during the summer season from May to October from flat plate solar collectors that he has on his roof. So uses of solar collectors, I've said heating hot water. Most people that use them to heat hot water don't actually use them to heat the hot water that they drink. Anybody have an idea for a use of hot water? Can you think of one that isn't drinking water? There it is. It is pool heating. We don't have too many pools here, but if you've ever lived in a climate where a lot of people do have pools and a hotter climate, you've probably seen things like this. So most people that use this kind of flat plate solar collectors are using it to heat the hot water in their pool. And here's an aerial view of what that looks like. When I really notice this is when I fly in to places in the Southwest. So if you've ever landed at, say, Phoenix or Las Vegas or any of those, or LA, any of those type of places, when you land in and you're kind of landing over a community that has lots and lots of um, pools in their backyard, you will also notice lots and lots of these things. And what these things are is it sucks the water out of the pool, it brings it up onto the roof, it cycles that water on top of the roof, and then it spits it back into the pool. So they're just ways to efficiently heat the temperature of your pool. And people have been using these. I went to high school in Las Vegas 20 years ago, and those were in heavy use in Las Vegas 20 years ago. So these have been sort of a cost-efficient way to heat water for a really long time. Another thing that we use is called a concentrating solar power plant. So concentrating solar power plants work a lot like a satellite dish. So the sun's rays come in and they can focus all of the rays that hit this whole satellite dish into a single point, which we call the focal point. And the idea here is more or less the same as making a fire with a magnifying glass. So here's what that looks like. Right, so the sun's radiation comes in from above and it focuses all in one spot. So you can make something very hot if it's placed at just the right location. I don't know if you ever did this as a kid. I know I did. This is hugely exciting as a child. You can burn all sorts of things and catch all sorts of things on fire. Probably good coronavirus activity. Most glasses, if you wear glasses, actually aren't the kind of lens that will do this. If you're farsighted, then you would have a pair of glasses that would do this. But if you're nearsighted, then you actually don't use the right kind of lens for this. But yeah, ants light on fire pretty easily. I'm not saying I ever did it, but I definitely saw it from plenty of friends as kids. Okay, so the reason I showed you that video is to show you, right, if you had some sort of fluid, say here, you could heat up a fluid in a big way. And so this is what we have entire power plants that instead of using PV solar panels like what we use here a lot, they are like garage door sized mirrors that are have this curved shape, and they focus all of the sun's energy into a single point. And right along this point is a tube of some sort of liquid that can just get really, really, really hot. Um, Another thing that you can do is this is a power plant, and all of these things are just mirrors, and all of these mirrors are focusing right here. It's called a power tower. So there's some sort of liquid inside the top of this power tower that's just getting hotter and hotter and hotter as all hundreds of these mirrors are focusing the sun's energy like that. This is the largest CSP, the concentrating solar power plant in the U.S. is out in the Mojave Desert in the Southwest. It uses almost 350,000 garage door sized mirrors. And this photo down here, like this is a mountain for scale down in the bottom of this. Right, there's a mountain. This is a huge power plant. Um, and I think just uh, Um, so I wanted to put this in here so that I could see some of my notes. So this is a huge power plant that takes up a ton of space, but this power plant actually produces zero point 0.4 gigawatts of electricity. And I like to think about things in terms of gigawatts because I want you to get to where you have this factoid in your head, which is that a typical um, gas or coal plant is about 1 gigawatt. Okay, so even this giant swath of mirrors out in the desert is only producing 40% of a typical power plant. And this is typical of solar, right? It takes a ton of space to have a power plant, a solar power plant that replaces actually any sort of traditional power plant. Okay, so let's talk about hydro. So I want to start out talking about hydro, maybe by raining on hydro just a little bit. So hydro is a renewable resource, right? And so it's something that we think highly of most of the time, right? It doesn't produce any, it's an energy flow, so right, we can never use it up. That's the definition of a renewable resource, right? Something that is an energy flow. And producing the electricity doesn't produce any greenhouse gases and all sorts of things like that. But I want to just profile probably the most controversial dam in the world, which is the Three Gorges Dam on the Yangtze River in China. So this is the largest hydro plant in the world. It's the largest dam in the world. And this is what it looks like. So this is called a low head dam. So it's a very wide dam that isn't super tall. And everything back here is a new lake that was formed. So when you put up a dam, like you stop the flow of the river, and it makes a lake behind the dam. So it doesn't always make a huge lake. So we have lots and lots of dams on the Hudson, and they don't always, make a lake behind it. But in this case, we made just a giant lake behind here. And you can also kind of get a view of, right, this is where the water is coming through. So the electricity is being produced right here. Right over here on the side is locks. So in these locks, a boat, right, used to be able to just go up through the middle of the river. Now it has a little channel right here. And we can allow fish and wildlife to potentially be able to pass through this dam, but of course also boats and ships and stuff like that as well. So here's what the satellite image of the area looked like before and after the dam. And so in addition to noticing this big lake that was formed, you can also see there's a lot of land use change that happened after it was formed. Right? So we've created some new lakefront property, which means that old property here has been flooded. There's another aerial photo of what it looked like. This is during and after. And this during, so this is sort of while they were building the dam, but before they actually had completed. Like it's all brown here. This is land that they basically had to just bulldoze. Because the last thing that you want to do is have like a skyscraper that a boat is going to go travel over and like get get a hole punched in it as it travels through that. Okay, so they had to just bulldoze huge areas in order to make this dam. Here's what that bulldozing looks like. So, right, this is the current location of the river, and this is going to be the bottom of the new reservoir that's formed by this dam. And you can see that this is very much was a like a place where people lived in China. And people all over the world, right? We live next to rivers. We live next to water. It's useful to live next to water, right? So that we have access to the water. People also just like living next to the water. So this is a pretty populated area. This is a city that was displaced, so Wanxian, China. I guess I want you to, like, what do you think the line is for? That line is the location of the water level in the reservoir. So this whole city had to be bulldozed and removed so that we could have a new reservoir at that height. These are new buildings that are being constructed to house the people that were displaced by this. So this is our future waterfront condo complex up here. So I think we've shown a few downsides of dam building. Okay, and I've profiled this Three Gorges Dam because it had a lot of downsides. So something I didn't talk too much about, but that should have been evident, is that this really alters a natural environment. So this is like a wild river issue, right? If you were a fish, you used to be able to pass through up and downstream on this river, and now maybe there is a route for you to get through, but it is a very different route. So in a high head dam, so this would be I'll show you what I mean by a high head dam in a minute. There's high head dams. And a high head dam, this is the Hoover Dam over here. It's a high head dam. Here's a dam in Oregon. It's a low head dam. Right, there is no way, this is a complete barricade. There's nothing that you can do to create a way for the ecosystem to remain similar upstream and downstream. Right, a fish now no longer is able to pass through. And a low head dam, you can create situations for letting fish get through. And I actually have a video of a low head dam and how and I'll show that in just a minute. So these two dams are very similar dams, right? They both generate over 2 gigawatts of hydroelectric power. So 2 gigawatts, right? That is twice a typical fossil fuel power plant. And so this was actually a reading quiz question. The answer to that reading quiz question is right. A hydro dam is the largest dam in the world, right? If we just put up a dam, the biggest hydro dams are way bigger than typical than any other power plant that exists. So in terms of being better, I wouldn't say strongly that one is better than the other. It depends on what you're looking for, right? If you don't want to severely alter the ecosystem, then a high head dam is probably quite a bit better. An advantage of a high head dam, say over a low head dam, might be the size of the reservoir that you create. So this dam, just judging by how tall it is going to make a really deep lake. So this really deep lake might make this really deep dam will make a really deep lake behind it. So maybe you can have a reservoir that doesn't take up as much space behind it. So that might be an advantage of a high head dam. But generally speaking, these low head dams have fewer environmental impacts. And so what I want to show you is a video of fish. So fish salmon in particular, are really big business out on the west coast of the US. So we're going to watch a video of a salmon run. So salmon are pretty crazy creatures. So they are born in freshwater lakes and rivers. This is actually a video about salmon that were born in a fishery. So they're sort of spawned, and then and then after they are babies, they leave and they go out into the ocean for a couple of years. And nobody really knows what salmon do when they're out in the middle of the ocean. They just live out in the middle of the ocean for a few years. And then when they are ready to die, they come back to the place where they were born, exactly the place where they were born, and they lay their eggs and they die. So they only reproduce one time in their lives. It's the very end of their life. And so they need to return to where they came from. So if you put up a dam on a river, an entire population of salmon will just die because they try to go and they can't get back to where they were before. So this is actually a fish ladder that was created at a Lowhead dam. So there's a dam here, right? There's the dam. And the fish need to get by. And so what was created is a fish ladder, and it's these little basically water steps so that the salmon can swim upstream to get back to the place where they were born so they can lay their eggs. And everybody that lives in the Northwest can fish for the salmon and continue their billion-dollar industry. So they're going to just like jump up the fish ladder. There's examples of fish ladders like this, many that are open to the public all over the West Coast. So if you ever get a chance to check one out, I definitely recommend going to see it. When the salmon are running, it's pretty impressive. So again, the reason I'm showing this video is to show an example of the type of innovation that we're doing to try to kind of minimize the environmental impacts of a dam, right? The impacts of a dam are still huge, but we can still, with the right dam design, have something that doesn't totally destroy an ecosystem. Okay, so let's go back here. Okay, so our downsides of dams, right? Travel by boat and by fish is impeded. This also blocks sediment flow. So the natural flow of rivers brings with it dirt. And that dirt tends to be nutrient rich dirt. So there's actually examples of places where dams have been, I think this happened in Egypt. They put up a dam and it prevented floods that used to happen every year downstream on that river. So now we had a dam, so we didn't need to have floods. But this was a place where farming happened. And so every year those floods used to deposit nutrient rich sediment on the ground, and it made it actually so that farmers were able to farm this land without using any fertilizer. It was just an annual replenishment of the nutrients that happened there. When they put up the dam, that completely stopped, and now this place that used to kind of be a pretty sustainable place to farm is gone the route of having to fertilize multiple times a year every year, and created a whole host of other problems because of it. So building dams displace people. So the Three Gorges Dam displaced 1.2 million people in over 100 cities and towns. So this is a pretty extreme example of a dam, but this has happened in New York State. So we have lots and lots of dams in New York State. And these are all towns that used to exist, but that don't exist because they were flooded by different dams that we've created. So I think, for many reasons, New York State is pretty much done putting up dams, and this is certainly one of them. Right? This might have flown 100 years ago before we all had access to instant news and social media. But right now, there's no way that I could imagine us building a new dam that would completely destroy a town. Right? A news agency would get in charge of that, and they would sort of broadcast people that didn't want to move having to move, and that would be over. Um, okay. Um, a couple more downsides is, right, dam failure. That's something that is rare, but that would obviously be pretty catastrophic. Um, Something that people don't talk about as much is that methane is emitted by a dam. So methane is similar to carbon dioxide in that it's a greenhouse gas that's responsible for global warming. Um, and methane is something that's produced when stuff rots, but it doesn't have any oxygen. So when things like old trees that are drowned by a dam rot underwater, instead of releasing carbon dioxide as they die, they will release methane. And methane is actually a much more potent greenhouse gas than carbon dioxide is. So it's something that we worry quite a bit about. So that's another possible downside of hydropower. So producing the electricity itself doesn't release any carbon dioxide, but the creation of that reservoir, and in some cases, the creation of the reservoir uh, has produced so many greenhouse gases that it's kind of comparable to the greenhouse gases emissions that would have come if you had a more traditional fossil fuel power plant there. Um, okay. And also, PV plants, we already talked about how they take up a ton of space. Often the power that you generated per square foot of solar PV can be better than hydro. So there's a bunch of downsides of hydro. I actually didn't say this yet, and it hasn't appeared on the slides yet, which makes me worried that it might not be on there. So I'm going to say it now. Right, this Three Gorges Dam seems like it has a lot of issues. So was it worth it? Why would we build a dam to do this? This single dam has 22 to 23, I think it's 22 and a half gigawatts of power. So that is replacing 22 coal-fired power plants. So the government in China decided that all of these negatives of the dam was worth it because they were able to stop, right, coal plants release all sorts of things that are toxic to you, right? They release particulates, they release mercury, they release gases like sulfur dioxide that produce acid rain and all sorts of stuff. Okay, so we already talked about the different types of dams. Up in Elwah, Washington, so this is in the very northwestern tip of the United States, there is a there's so like west of Seattle, so almost all the way to the Pacific Ocean. They just recently removed a high head dam. So this is what the dam used to look like. There's a reservoir back here that was created by this dam, and they went out and they took it out. So this is what it looked like right after they removed the dam. So there used to be no way for the river for salmon and other river creatures to travel back and forth, and now it has. And they actually went and they reintroduced salmon. So there had been a native population of salmon that used to spawn in this river, but those salmon have died back. But they've reintroduced some new salmon to do this, and they've been getting salmon runs and have returned to a more wild river than the way that it used to be. Actually, another crazy thing about salmon is, since I'm just apparently in love with salmon and can't stop talking about them today, is that they will be unique to the river that they come from, right? So since they always return to the spot where they were born, like Chinook salmon are salmon that come from the Chinook River. So there's different species of salmon that are named by the river where they come from, which is pretty cool. That's not true of all salmon. There's some salmon that are in many different rivers. So right, the kind of salmon that they reintroduced into this river is a kind of salmon that exists elsewhere. But yeah, and actually, um, the rivers that are more treacherous to travel through, those will be the rivers that have the super high quality salmon, because you have to, right, as that video said, like on their trek up the river, the salmon don't even eat. So they have to have enough fat on them when they enter the river to make it all the way up the river. So if it's a really treacherous route, then they have to be very, very meaty and fatty to start off with. And we really enjoy the taste of meaty, fatty salmon. So it's the salmon that have the hardest job ahead of them that are the highest quality salmon and the most expensive salmon. So there's some towns. Okay, so I have just spent this entire portion talking about why hydro is bad. And I really hope that you don't leave this class today thinking that hydro is bad and that we should never build a dam. Right? There are very real reasons why we build a dam. The first is, right, this is getting off of fossil fuels. So this is a renewable energy source that is fossil fuel free. This is also a huge power capacity. Okay, so this dam is over 2 large coal plants. And this is the largest in the world, but it is not uncommon to have a single dam that's 2, 3, 4, 5, 6, even 7 gigawatts. So these are single structures that can have huge, huge power supports. They're also highly efficient. So most power plants operate by turning heat into electricity. And as we've stressed over this semester, anytime you're turning a high entropy and highly disordered energy like heat into a low entropy and low disorder kind of energy like electricity, you can't do that very efficiently and you waste a lot of that energy. But in a dam, all we are doing is turning the energy of the flow of the river. So this would be kinetic energy or gravitational potential energy to lower the level of the water into electricity. So this can be something, a dam can be 95% efficient at turning the energy of the flowing river into electricity. Unlike maybe every, no, not every, but just about every renewable resource, dams don't have much of an intermittency problem. Okay, so solar and wind, right? Sun's not out, the wind's not blowing, that resource is off. But rivers always continue to flow. Recreation is another big part of this, and this is true in New York State. It's true everywhere that we have a lot of dams. Like this is an industry that supplies local communities with money and business and opportunities for jobs. So right, people like to fish in reservoirs. People do boats and they do water skiing and all sorts of activities happen in the reservoirs that are created by these dams. Another idea here is the idea for storage. So we have stressed, right, that solar has this intermittency problem. So one idea that people have is that why don't we use hydro as a way to store energy instead of using, say, a battery. So we talked last time about how batteries are kind of prohibitively expensive. Even though the cost for batteries comes way, way, way down, we're never going to use batteries to just solve the whole problem with the intermittency of renewables. Here is a pumped storage. So the dam is actually all the way down here. So the dam is down here, and what is going on is that over the course of the day, rather than having this dam produce electricity, what this dam is doing is it is taking the energy from the flowing river and using it to pump water up to the top of this mountain. And now we've created a lake on the top of the mountain. And you know what I see when I see this lake? I see gravitational potential energy. I see very heavy water that's being stored up at the top of the mountain. So that has energy, and we could take that energy and turn it into electricity. So this is a giant battery, right? So during the day when the sun is shining, instead of getting electricity from the flowing river down here, we are just pumping water up to the top of a hill. At night, the sun goes down, solar turns off. Well, now we can run this water back down to here through our dam, and as the water runs through our dam, we can use that to create electricity. So this is a nice way to complement intermittent resources with another renewable resource. So I also talked about removing this dam, and there were pluses and minuses to removing this Elwah dam. So dams, and this is a big part, this is big in our area, right? They provide defense against floods and droughts, right? So flooding happens every year on the Hudson River, but flooding is really substantially mitigated by the presence of our dams that we have on the Hudson River, right? So we'll do kind of if there's too much water, we're sort of plug up some water to try to prevent flooding from happening downstream. And we can manage how much water flows through the Hudson in this way. So if you think we have a flooding problem from the Hudson River now, you should see what the flooding would be like if we didn't have dams to help control the river flow. And actually, this photo here is a photo of a road that washed out in the years right after they removed the Elwah Dam. So there was additional floods. Also, droughts. So if you have a big reservoir, you can store water in it. That helps kind of mitigate the effects of droughts. And both floods and droughts, for reasons that we will talk about later in this semester, are things that will probably get worse into the future. So it may seem like a impossibility. So I guess I'll just leave you with that for the next few weeks until we get to talk about it in class. But actually, in a warmer climate, we expect most places in the world to experience both floods and droughts. So when it rains harder, but when it rains, you have to wait longer until the next time. Okay, New York is a big hydro state. So this is the dam up by Niagara Falls. So this is a 2.4 gigawatt dam. We share a series of dams with Canada right up there. In 2014 and probably future years, but this website that I get this data from hasn't been updated since 2014. New York produced more hydro than any other state on this side of the Rocky Mountains. So we are a big producer of hydroelectricity. Here's some more facts about New York. We have more than 300 hydro generating stations. Some of these are very small. You might recognize this one. This is Cohoes right here. So this is right along the background. So this is a 38 megawatt. So that's 0.038 gigawatts. So this is a tiny little power plant, but it's a generating station that produces electricity for many people that live in Cohoes. All in all, this produces 17% of our state's total electricity. So hydro is big business. Down here, growth. I've already talked a little bit about growth and why I don't think, right, we can't dam just because flooding towns would be a difficult thing to get through in terms of public opinion. Another reason that we're pretty much done with dams in New York State is that we are already all dammed up. Right? We've put dams everywhere. We are already utilizing that resource just about to the extent that we can. So a huge increase in hydro, and this will be a test question at some point, right? We can't ramp up our hydro much from where it is right now. So this is a figure from your book that is estimating how much hydro potential, that's the green bar, you have compared to how much hydro you actually are getting. So less developed continents like Africa here, they get a lot, they don't have as many dams, so they're not using a lot of their resource. Over here in North America, right, we are using half of the resource. And I love this statistic, right? We are currently using 10% of all of the energy from the world's rivers flowing to generate electricity. So there's a pretty big upper limit on how much hydro we can do to power the world, right? We don't have enough hydropower to power the world. Right? We do have enough sun to power the world many times over. Hydro is a different story. And in developed nations like the US and New York State in particular, right, we don't have much potential for growth because we have already grown as much as we can. Okay, so electricity from the wind. I am actually going to stop this video and I will come back and cover that in the next one.